Good day everyone. I'm going to discuss about optical photometry, its fluxes, photometric system, photometry CCD, atmospheric extinction, and astrometry with CCD. Optical photometry measures the apparent brightness of celestial objects in the optical region of the spectrum. The magnitudes and the colors of the stars and galaxies allow to derive their physical properties and composition. Photometry is a form of very low resolution spectroscopy, since it measures the spectra of sources in a few points, determined by the passband of the filters. We will present the procedures to extract the magnitude of an object according to this equation, where m sub o and f sub o are the 0-point magnitude and the reference flux. So we have here the apparent magnitude of some objects of interest to provide an estimate of the orders of magnitude. The power of photometric observations is demonstrated by the color magnitude diagrams, the graph of the absolute magnitude in one band against the color, the difference of the magnitudes in two bands. Generally, the diagram reports the V magnitude and the BV color. The position on the diagram provides information on the star type. BV color corresponds to the blue filter, while V corresponds to the greenish filter. Very hot stars have negative BV colors, and cool stars emit most of their light in red part of the spectrum. And so for the photometric system, the definition of a photometric system requires a detector, a set of standard photometric filters, and a group of standard stars with known magnitude and colors. Photometric filters are defined by a transmission curve P, function of lambda, each filter is characterized by an effective wavelength, where F sub lambda is the monochromatic flux. The difference in the magnitudes measured between two filters defined by the wavelength lambda lower and lambda upper is named color index, or mainly color. The photometric system are classified into three families. One is the broadband filter, widths of order of some hundreds angstrom, intermediate band, widths in the range of 70 to 400 angstrom, and the last one is the narrow band with widths smaller than 70 angstrom. Broadband systems are widely used, so we will focus on it more. The first photometric system is the visual band. It is defined by the response of the human eye. The peak frequency is in the region 515 to 550 nanometers with a width of 82 to 106 nanometers. The photographic band has a high transmission in the blue region at about 400 nanometer and a width of about 170 nanometer. Photovisual band is realized with the addition of a yellow filter to reproduce the visual band. The peak wavelength is about 550 nanometer, while the width is about 100 nanometer. The next one is the Johnson UBV system, defined using the blue sensitive photomultiplier RCA1P21 and a set of colored glass filters. Excuse me. The V band was defined to approximate the photovisual band. V, the V band to approximate the photographic band, and the U band to fill the region at the lower wavelength. So we have here the figure passbands of the UBV filters compared with the normalized spectrum of Vega. So the development of new photomultipliers sensitive to the red part of the spectrum has allowed the definition of Johnson RI system with the RJ band and IJ band in the red and close infrared regions. Another system in the red region based on the gallium arsenide tube is the Cousins RI system with RC and IC bands. The actual system is called Johnson-Cousin UBVRI system. And the next one is Sloan Digital Sky Survey, or SDSS, is performing photometric observations of stars and galaxies with the potential to become the future reference with an archive with about 10 to the power of 8 objects. So we have here the figure of transmission curve of the UBVRI and SDSS system. The HST WFPC2 has been defined for the Hubble Space Telescope. Among the several broadband filters, the bands F336, F439, F555, and F675 and F814 are partially related to the UBVR filters. Hipparcos-Tycho system has been used for photometry and astrometry of the hundreds of thousand stars investigated by the Hipparcos mission. And we have here the figure of transmission curve of the UBVRI and SDSS system, effective wavelength and bandpass width of some widely used band system. This is the properties of the broadband system, briefly summarized in this table. And due to the relevance of the UBVRI system, we report the flux corresponding to magnitude 0 in this table, flux magnitude 0 for the UBVRI photometric system. The intermediate band system have been devised to overcome the overlap of the bands associated with the broadband systems. The most widely used among them is the Strom-Grant system, with the UBVY bands well separated in response, useful for stellar temperature investigations. Transmission curves. We have here transmission curves reported here in the figure. We have the effective wavelength and bandpass width of the UBVY system and the transmission curves of the Strom-Grant system. Photometry CCD. Photometry requires photometric nights with cloud-free skies. Photometry with CCDs requires that data are calibrated for each observing night. In addition to science frames, it is necessary to secure different set of frames. We have the first is the bias frames, also called zero frames. Are secured with closed shutter and a negligible integration time to measure the CCD noise. Bias frames must be secured for all night of observation. An alternative to securing bias frames is the use of overscan, a CCD region that is not illuminated. However, the bias frames estimate the noise over the whole frame, while the dark frames are secured with closed shutter with an integration time identical to the exposure time of the science object to estimate the contribution of the dark current. The CCDs at professional observatories are cooled, thus it is not necessary to acquire dark frames. For the flat frames, we are secured using a source with uniform illumination to estimate the efficiency of the CCD pixel by pixel. It is necessary to secure that flat frames for all filters that have been used during observations. It is necessary to secure several bias and flat frames, at least 10 of each kind, to improve the precision. The individual bias and flat frames are combined using the mean or the median pixel by pixel to build the master bias and the master flat. So we have here the left image shows fluctuations about a mean value, which is a bias frame, and the right image shows a flat frame. The peculiar objects with a donut shape are the result of the um, diffraction on the dust grains inside the instrumentation. Dome flats are secured pointing the telescope out of focus towards a white screen inside the dome, illuminated by a lamp with a continuous spectrum, and while the twilight sky flats are secured at the twilight or at dawn, pointing to some specific sky regions with a small luminosity gradient. The choice of flat strategy is determined by the characteristics of the science target. The dome flats have a high signal-to-noise ratio, but the spectrum of the lamp is different from the spectrum of the sky, so generally being redder. Sky flats have a color with a better match, but the signal-to-noise ratio is lower. So the sky spectrum is affected by the variable contribution of the moon that makes flat frames bluer. So the choice of sky flat is for bright objects, while choice of sky flats mm, for fainter object. Dome flats rather. The choice of dome flats is for bright object, while the choice of sky flats is for fainter object. The reduction of raw imaging data requires several steps. Number one is subtraction of the bias frame from the object raw frame. 2. Subtraction of the bias frame from the flat frame. 3 is the normalization of the bias subtracted flat frame to its mean or median value. And 4 is division of the bias subtracted science frame with the bias subtracted and normalized flat field. That is summarized by this equation. CCDs are sensitive to cosmic rays arriving during the exposure time. They appear as hot pixels with high saturated counts. They can be removed by an average of the near pixel values with sigma clipping technique. So, statistical properties of the bias and the flat frames are related to the CCD characteristic, the gain G, and the readout noise RON. So the histogram of the pixel counts of bias frames and of flat frames are both Gaussians, with the standard deviations sigma bias, where f is the mean value of the flat field. An estimation of the gain and of the readout noise of the CCD can be performed during a pair of bias frames B1 and B2 and a pair of flat frames F1 and F2. The extraction of magnitudes is performed with two main techniques. First one is the aperture photometry. It is the signal of the object extracted within an aperture, usually circular around the object, mimicking the approach of photoelectric photometry. So, in the method of aperture photometry, a region called aperture is drawn around the star to enclose the most part of the light. Then the radius of the aperture should in principle contain the whole light from the star. For bright source, large radii are a better choice, but they will not contain the whole light from the star. Next is the point spread function fitting photometry. The profile of each source is fitted with a suitable point spread function that is identical apart the amplitude for all stars in the same frame. It is applied when stars overlap or several faint stars are present, relying on the uniformity of the point function for all stars in the frame. Some examples of analytical point spread function fitting photometry is the Gaussian function I and the Moffat function describing the same profile I. So it is possible to define an empirical PSF or an analytical PSF. PSF is built choosing some bright stars in the frame and modeling it with a combination of a Gaussian and some residuals. The fitting of the PSF is performed within a defined fitting radius. Generally, the data reduction softwares simultaneously fit several stars at a time. The reduction of photometric data requires two important steps. First is correction of the effects of atmosphere of the extinction and the conversion to a standard photometric system. A fundamental ingredient of the photometric system is a set of standard stars, whose magnitude and colors have been measured with high precision. So a standard star should be non-variable and should be available in any sky region targeted for observation. They should be distributed over large intervals of colors. Next is atmospheric extinction. So we recall the radiation is affected by the interstellar medium that attenuates and also scatters the radiation, producing the interstellar extinction. The color axis is defined as BV is equal to BV minus BV of 0, where the index 0 labels the intrinsic values. The interstellar reddening law relates the interstellar absorption AV in the V band and the color axis BV. So we have here the figure of the interstellar reddening law. The radiation collected by a ground-based instrument is affected by the absorption and scattering of the incident radiation in the atmosphere. The path in the the path in the atmosphere is the product of the vertical depth of the atmosphere and of the air mass x, a function of the zenith angle z. The air mass is 1 for object at zenith and 2 at the zenith distance of 60 degrees. The combined effects of absorption and scattering of radiation in atmosphere produces the extinction. So the extinction depends on the elevation of the object above the horizon. Object and brighter Object is brighter when it is higher in the sky, being brightest when at zenith. The extinction is the optical region measures at two astronomical sites is shown in this figure. So we have here the atmospheric extinction at the QPNO and CPIO observatories. Assuming to work with the monochromatic magnitudes, the value m observed with the ground-based instrumentation depends on the value m sub o measured outside the atmosphere and on the air mass x according to the Boger law. So where k is the extinction coefficient, assuming to monitor a star at different air masses. The extinction coefficient is estimated by the slope of the straight line of the graph of the observed magnitude m against the air mass. And for the astrometry with CCD, the CCDs are currently used for relative astrometry to determine the relative positions and the proper motion of stars with respect to reference object in the same frame. The astrometric observations involve securing photometric observations of the desired fields at different epochs, extracting each time the position of the stars and of the reference object. The bias due to the average motion and parallax of the reference frame are subtracted from the observed positions. Astronomy is necessary anytime a new transit is discovered. Photometric observations with high signal-to-noise ratio provide a precise estimation of the aperture photometry or point spread function photometry. And block illuminated CCDs are preferred for astrometric observations since they have a better blue response and no subpixel variations caused by the penetration through the electrodes. So that is all for my report. Thank you so much for listening.